So what I'm gonna do is give me a second. Fuck. Whew, thank God. It's like, yeah, there are times I'm like sick. Just talking shit, racist shit. That's not fun, but it's like, hello. Yeah, not bad. I'm gonna do a little fast today for the next couple of days. Fasting. I'm gonna do a little fasting. I'm really fucking fat for some reason. I don't know why. Yeah. I stopped training. I stopped training like a couple of months ago, and I was like, huh? Various reasons, mainly, yeah, various reasons. Yeah, stop training. Now I'm kind of like fat. I need to get like kind of jacked before I come to India. So I'm on a 3-day fast. Hopefully, I think it's gonna be like really fuck my mood up and whatnot. But hopefully I can like pull through. Yeah, I'm gonna need it. It's gonna be really difficult. Yeah, just water fast. It has like little to like no like cognitive benefits as far I can tell, but yeah, it can like burn off some serious fat. And obviously, I don't know if I'm gonna work out or not. Maybe not. It's gonna like fatigue me so much if I try to like working out. Yeah, obviously. Yeah. Ideally, I think like the best thing to do is like eat like normally and like work out like a maniac. And I mean that's what I've been doing the past couple of years. Yeah. I think I've never had like an issue with like weight for like the past couple of years. Now I'm like sitting around. Yeah. I was kind of like fat when I was like. You remember like when we used to like sit together? I used to like have a fat ass. Never. I mean, I was kind of fat when I was like 14, 15. Kinda. Not like too much. Skinny fat. Skinny fat would be the. Yeah, I mean that's me too. You know, that's like the Indian genetics. Especially you see like I mean I'm kind of like around the white guys a lot. It's like when they get fat, they get like the fat deposit like goes. No, the fat deposit like stores in their arms and the legs. Like you know what I mean? Like they look even though they're like the same body fat percentage, they still kind of look jacked. Even though we're like the same body fat. That if you know what I mean. It's like when we get when we get fat, it's in the belly first, the ass second, and the face third. So we are having skinny little arms and like fat little bodies. It's just, yeah, it's just like a curse. But I think I do have like a pretty long arms, so it's even worse if I get like fat. It's like a lanky little arm and like fat little body. Yeah, I just like, I don't know. I was just like in my room all day, just like looking at screens. No physical activity. Putting on some pounds. I mean, yeah, it is what it is. But definitely, like, if I get the rhythm going on, I can get it back on. So, anyways, what you gonna do now? Yeah, yeah. Hmm. Hmm. Yeah. All right, bro. I'm gonna mute myself and let's get walking. Okay. Ha ha ha.
Down the text into tokens. You can then use the vocabulary to convert these tokens into
Hey everyone, welcome to this full 5-hour deep dive into the world of convolutional neural networks. In this course, we're going to break down the evolutions of CNNs from the early days of LeNet and AlexNet all the way to cutting-edge models like ResNet, Inception, and even Vision Transformers. But this isn't just a history lesson. We'll uncover why these models were built the way they are, what problems they solved, and how they changed the game in computer vision. Whether you're new to deep learning or sharpening your skills, this tutorial will guide you step by step with explanations, visuals, and real-world insights. So grab your coffee
IDs.
and let's dive in.
And then there's also
What if I told you that every neural network architecture, LeNet to Vision Transformers,
a reverse function. It's this tokenizer decode method, and this method will take token IDs. So when we have token IDs here, convert it back into these token strings, and then assemble the token strings back into text. So you go from basically text to token IDs, and then back from token IDs.
So yeah, I think this kind of like tokenizing, what is it seen? Fuck is watching. How do I? Anyways. So tokenization. So anyways, let's
to text. So I can maybe just show you how this works here. So if I initialize a tokenizer, simple tokenizer version 1, I give it the vocabulary.
what am I doing wrong? Simple tokenizer. So we have, oh, what the hell? So this code over here is simple tokenizer, and the first one over here is initializing string to input. So we are decoding and encoding at the same time. String to input is equal to vocab, or the vocab is going to be string to input. Okay, input to string. Okay, string to integer. That will be the vocab. Everything in the vocab is string to integer, and I want to print out. It's going to print out all of the tokens. So let's print. What happened? Okay, anyways. So that is this encode will be self.text. So we're giving it text. Don't know what the text is. It's just like a placeholder value. Process split.
Let's say vocab, right? May have to execute. I did execute this. Okay, it should be fine. So I should need to execute this first, of course. So now when we initialize this tokenizer with this init method, it will store the vocabulary string to integer. So this is the vocabulary we use to map from string to integer that we already created. And then we can also have a reverse vocabulary. So this maps from integer to string. So here it's essentially just reversing it. So instead of string integer, we have integer string. So just to show you how it looks like, let's go maybe here. So I have my vocab that maps from string to integer, and I can say integer string for string integer in vocab. Oops. Keep hitting this down button for some reason. And this should be items, I think, because otherwise I will iterate over the keys. This should work. Yep. So this is now essentially the reverse mapping from integers to the strings.
So we have ordered. Is it ordered, or is it 0 is equal to listing 1, 2, 3? I don't know how the n kind of like snuck up on it, but anyways, it's ascending order, whatever. Cool. How do I delete this? Delete.
Okay, and so this happens when we initialize it, so it constructs this, and then we can use the encode method. The encode method that can then convert our text into token IDs. So let me from the top grab some. I can actually also go here. Let's just scroll down here. Sorry for scrolling so much. So I can go here to the verdict. Let's just copy some text here and tokenize this text. So here I'm going to tokenize it, and yeah, you see we have these integers now, and I can do the same thing in reverse. So I can take this and say tokenizer decode, and this will be just doing the same thing but the other way around. So we go now from the token IDs to this text. Here, and this will be just doing the same thing, but the other way around. So we go now from the token IDs to this text here. And yeah, this is essentially how the tokenizer works. So we have a method and
So this is regex. So regex. Should I learn regex? I don't know. If I want to work on VLMs, should I learn regex? Probably not, but a little not not first. VLMs, vision language models. Is vision language models still being used? Is vision language models still being used? Mm, so if it is, if I, oh, I don't know what it means. Ooh, wait, no way. So I need to learn vision language model for sure. Let's. I don't know what join means. So let's. I don't know. Let's see. No. Fuck. Fuck. Please don't make me beat the fuck out of you. For Python, RE model is a one or more. Anyways, should I learn it? Probably not. Uh, White space characters. Okay, let me get a pen. Let me get a pen. Let me get a pen. Can I get a pen, please? I need to do a one for ML. Anyways, one or more white space characters tabs capturing a group. Why is it? So what is regex? The important building blocks. Characters matches A can. Okay, matches A matches cat. Set A, B, or C or any digit lowercase a lowercase letters. Special shortcuts digits W word white space dots grouping capture a number with examples, please. Find all. What do we use? Ferrari. The fuck do we use? Substitute all of that with this. Okay, whatever. It's regex. It's kind of useful, kind of in the tokenizer. Okay, it's all already in there. So what kind of It contains text tokenizers, image tokenizers, converts image into tokens and embeddings. Text tokenizers, same as LLMs, BEE. Do all text tokenizers is using regex question mark. Short answer, sometimes yes, but not really the way you think. But they're a little, but they often use a little help as what do they actually use? What preprocessing, BPE, byte pairing, encoding, all these encoding methods. Interesting. Anyways, let's no, don't do that. Byte pair encoding tokenizer. Okay, it's a thing. Anyways, um,
Are trained. First of all, we have to get a corpus of text. We will not train our tokenizer on this raw text, but we will first normalize it, then pre-tokenize it. As the pre-tokenization divides the text into a list of words, we can represent the corpus in another way by gathering together the same words and by maintaining a counter, here represented in blue. To understand how the train
In this lecture, we introduce a byte pair. In this lecture, we introduce a byte pair encoding or BPE algorithm, which uses corpus statistics to decide how to segment the text into tokens. Instead of just breaking up words at every white space, or as we saw for Chinese, breaking up words at every character, the algorithms we're going to introduce now use the data to tell us how to tokenize. And this family of algorithms is often called subword tokenizations because the tokens can be parts of words as well as whole words. There are three common subword tokenizations. In this lecture, we introduce a byte pair encoding. In this lecture, we introduce a byte pair encoding or BPE, which we'll talk about now, an algorithm often called Unigram for Unigram Language Model Tokenization, and the word piece algorithm. These algorithms all have two parts. First, a token learner that takes a training corpus and induces a vocabulary set of tokens that is the vocabulary that the tokenizer will try to map things into. And then the second part is a token segmenter that takes a test sentence and tokenizes it according to the vocabulary it learned from the training corpus. So let's start by talking about the first part, the token learner. Let's imagine that we start with a vocabulary that is the set of all individual characters. So maybe we have all the capital letters and all the lowercase letters. That's our vocabulary. And we're going to repeat the following k times. We first choose the two symbols that are most frequently adjacent in the training corpus, two letters that occur most often next.
code that goes from text to token IDs, and then we have the other way. We go from token IDs back into text. Okay, yeah, this is our simple tokenizer. I already showed you this, so nothing new here. And now I should say, I mean, there's a reason why I called it simple tokenizer version 1. This is really just a very naive, simple tokenizer. It's to illustrate the two concepts of encode and decode. Now in practice, when you use a LLM or a tokenizer, you usually, when you use an existing LLM, you use a pre-trained tokenizer. So when you are creating a new LLM, there's actually a training for the tokenizer where you are applying the tokenizer to a data set, to the training data set, and then it learns a vocabulary, like similar to what we have done before. Now, in practice, there are more sophisticated algorithms for that, and one of them is called byte pair encoding. And what's special about byte pair encoding is that it can handle unknown words. So in this workshop, because this would be another 4 hours implementing byte pair encoding and training it from scratch, we are going to use the tick token library, which is an open source library from OpenAI that is very popular and is used to, tokenize text for GPT type models. It's pretty fast, so it's a Python library, but it is implemented in Rust under the hood. And I compared it to some other implementations, for example, the original byte pair encoder by OpenAI that was used for GPT-2. And it was 3 times faster than that. And I compared it also to the BPE tokenizer in Hugging Face, and tick token was 6 times faster. So it's much faster than, let's say, the Hugging Face tokenizer. So that's why we are going to use this particular tokenizer. It's a nice fast tokenizer, and I will show you in a moment how it works. So first we are going to use the GPT-2 version of that, and then really the way it works is very similar to the way we used it before. Also, we used our own simple version 1 tokenizer. So there's also an encode method and a decode method. And it's essentially the same input, so it takes text.
Hello and welcome to this video on tokenization. Tokenization is...
Let's start with byte pair encoding tokenizer, commonly abbreviated as BPE, which is a subword tokenization algorithm that recursively merges the most frequent pairs of consecutive bytes or characters in a corpus. For instance, imagine that we have the following sentence: Deep Learning Engineer. The first step that the BPE encoding does is to pre-tokenize the sentence by splitting the text into words, resulting in 3 words with frequency 1 in our case: Deep, Learning, and Engineer. Now, we initialize the vocabulary with all the individual characters found in the sentence, and if we were to tokenize it, we would get the following: characters divided by space. Then, we iteratively merge the most frequent pair of characters, which in our case is either in or EE, and add the merge group into the vocabulary. Let's say that we choose to add in. Now, if we were to tokenize the sentence again, using the vocabulary, we would obtain the following. We can see that both the word learning and engineer are tokenized differently and now include the in pair of characters. Next, we repeat the process and merge the tokens again and calculate the frequencies, resulting in EE having the highest frequency. So we add it to the vocabulary. Now, if we were to tokenize the sentence with the updated vocabulary, we obtain the following. We can see that both in and EE are now treated as separate tokens, which is what we expect. And again, this process of merging tokens together based on the highest frequencies is repeated until we reach the desired predefined vocabulary size. Moving on to the word piece tokenizer, which is very similar to the BPE encoding in the sense that it first initializes the vocabulary to include every character present in the training data and progressively learns a given number of merge rules. However, in contrast to BPE,
WordPiece does not choose the most frequent symbol pair, but the one that maximizes the likelihood of the training data once added to the vocabulary. So what does this mean more exactly? Referring to the previous example, maximizing the likelihood of the training data is equivalent to finding the tokens pair, whose probability divided by the probabilities of its first token, followed by its second token, is the greatest among all token pairs. And if we were to compute that, we would obtain the following probability, and pick either the EE or IN pairs, or, in addition to BPE encoding, due to the way probabilities work here, the NG pair, since it also has the highest likelihood. And again, the rest of the algorithm is the same as in the BPE tokenizer, the only difference being that we replace the merging criterion from frequency to maximum likelihood. Finally, the previous subword implementation assumed that the input sentences are pre-tokenized, a constraint that is usually required for efficient training, but makes the pre-processing complicated as we have to run language-dependent tokenizers in advance. What do I mean by that? Well, imagine that we want to use the BPE encoding for Japanese or Chinese, where no explicit space exists between words. So you'd have to implement different pre-tokenizers for such languages. Well, the sentence-based tokenizer tries to solve this issue by treating the input text as a stream of characters, white space included, and it does that by employing the same merging algorithm as in BPE for the Unigram tokenizer, which works the other way around and initializes its base vocabulary to a large number of tokens, and then progressively trims down each token.
Whenever you chat. Hello guys, you're welcome to Dean's Tech class.
If you have spent any amount of time working with
We'll use a glue. We'll use.
Next, I want to introduce you to the TikToken library from OpenAI, which is the official library for tokenization from OpenAI. So this is TikToken. Pip install TikToken.
Ooh, the synchronicity is crazy.
You need to choose the right
encodes it into integers, and then it takes integers and decodes it back into text.
So what is happening here? TikToken import lib. I don't know what import lib is. TikToken version. Anyways, let's try this out. TikToken. Sounds a little python and pip install token in ipn, okay, whatever, ipy kernel. Anyways,
just to show it to you here. And one thing maybe I should mention is this part. And so there is another specific token called end of text token. And this is a token used by GPT models to denote when a text ends and when a new text starts. So for example, when you are preparing a training data set, you may have multiple books. Usually, for example, when people trained the Llama 3 model, they used 15 trillion tokens, like many websites and books and so forth. And so usually you would insert this end of text token if you train a GPT-like model after each document or each book or website or so forth. So this is really just a text delimiter. And here I'm just showing you that in this particular case for tick token, it's not included for some reason in the standard GPT-2 encoding vocabulary. For some reason you have to explicitly add it here. And this will be then corresponding to the 50,257th token, because in PyTorch or in Python we start with 0 indexing, so we have 50,257 tokens in this BPE tokenizer. One thing that is special also about BPE compared to our own tokenizer is that it can handle unknown words. So what I mean is I could technically go here and say tokenizer encode and then some really made up text, and it will still work. So here in this case it will still work. I can, for example, say tokenizer to find out what these IDs correspond to. Say decode, and let's take the first one is 292. So I'm just taking this token here, and let's see what this decodes to. So it's actually considering this as a token, the AS, and for the second one, it's considering DK. So how it works is essentially that each character can be a single token if it's like this, where it's like an unknown word. But if the model has seen words before that look similar, for example S or DK, then it will use 2 character tokens. So in other words, what I'm trying to say is it can handle unknown words, but by breaking them down into individual parts. There's actually a quite interesting algorithm behind this. I'm not covering it here because yeah, it would be a long lecture, but it might be an interesting future video sometime. But yeah, we are going to use this BPE tokenizer for all the remaining sections in this workshop. So one more thing I wanted to briefly cover is the data loading. Yeah, because I don't want to spend like 5 hours of your time on preparing the data set. I will not go into too much detail of how the data loading is implemented here in this particular workshop. But one thing I think we should talk about is how the data is roughly structured. And so LLMs, when they are pre-trained, they learn to predict one word at a time. So if I have some input text here in blue, it would generate the next word here in red, the learn. So LLMs learn. And then for the next input, LLMs learn, it would generate the next word. And this is usually how we talk about, let's say, the LLM pre-training, the next word prediction task, and so forth. But what really happens under the hood is the LLM predicts the +1th token at each position. So it's maybe more clear if I show you this figure here. So here I have some input text, and in blue this would be my input. I'm not showing you so the LLM would see the token IDs, which are then embedded, but I'm showing you the text here because it's a bit more readable. So here, let's say we have input text instead of token IDs, so because then you can better visualize it. So the first input, if I have a context size of 4, would be in the heart of, and then the target. Targets, the thing that I want to predict is the inputs shifted by 1 position to the right. So you can see in blue that's the input, and in red that's the targets shifted by 1 position to the right. Right. So LLMs are really trained, let's say, on target tokens that are shifted by 1 position. So if I feed the LLM this input, it should generate this output. And how I get this next word at a time here that I'm showing you here is by taking only the last token. So for example, if I have this input, the model generates this output, I would only consider this last token here, the basically. So in this case, in the heart of so we have 1 more token, and then the next input would be everything shifted again by 1 block. So in pre-training, we could move over this blue one here, like I'm showing you here, by 1 position, and then we can have the next input batch like this. So we have in the heart, and the next input would be in the heart of in the heart of, and then the heart of the, and then heart of the city stood, and so forth. So we can always move over by 1 position, but then you notice that we get these overlaps, right? So we have the heart of here, and we have it here too. So in this case, the LLM would essentially see a lot of repeated tokens when you're pre-training it. So in practice, when we prepare the inputs, what we do is we shift this input window by the size of the input window. So this is also called called a stride. Sometimes, if you have worked with with CNNs, convolutional networks, you may be familiar with the strides when we talk about the convolutional kernels. Here it's a relatively similar context or concept. So here, if we have an input of size 4, for one training example, we would then move it over by 4 for the next one, so that we don't have an overlap for the inputs. The targets, I'm not showing you the targets here because it would be too cluttered, but the targets are still shifted always by +1, because you always want to predict the next word. There are actually some LLMs, there's one, actually it's only one, it's called multi-token prediction something. So there was a paper recently by, I think it was Meta AI, who developed a method to predict 4 tokens. But this is really like an experimental research paper. In practice, if you look at all the popular LLMs, for example, ChatGPT, GPT-4, Llama 3, Phi 3, Gemma, and so forth, and Gemini, they all do next word prediction. So it's a sense like the targets are shifted by a position of 1. And we will actually also see sampling function later once we pre-train the network. So then it will be also a bit more clear how you get that next token in case this was confusing. The last thing is I wanted to briefly show you just how the data set looks like. I originally planned to go over this, but this ended up being too much material, because I think we are already talking for half an hour just about this section, and there is also still the architecture and the pre-training, weight loading, and fine-tuning to talk about. So I'm cutting it short here, and I will just mention there is this function I implemented, which will then essentially produce the input batches for the model. So here in this case, these are the inputs, and these are the targets. So the inputs are the token IDs here. I mentioned I'm showing you the words instead of token IDs because it's more readable. Got the same concept here. So you have an input and then the target shifted by 1 position. So you can see the 367 here, and it's located right here, and then 285, 2885, and so forth. So everything is shifted by 1 position, and you can also see that there's no overlap between any of those. So in case you are wondering about that, it's basically this moving over by 1 position. By the size, by 4 positions. And here we are using this max length of 4. So we have